All right, let's give you guys a little bit of practice with using Henderson-Hasselbalch. Let's calculate the pH of the following solution. And this is going to be a buffered solution, 25 milliliters of 0.150 molar HClO hypochlorous acid. You should know also that sometimes they write it like this, HOCl. Okay, same thing, hypochlorous. And 32 milliliters of 0.45 molar KOCl. Same thing here, okay? And Ka values, 3.5 times 10 to the negative 8. My reaction here is just going to be the dissociation reaction of the hypochlorous acid. So HClO dissociating into hydrogen, ClO minus. Okay, go through, figure out millimoles, use Henderson-Hasselbalch to calculate pH. You should be getting 3.75 millimoles of HClO, and you should be getting 14.4 millimoles of KOCl. And knowing that I can just use millimoles to plug into Henderson-Hasselbalch, my pH is equal to my pKa, which is the negative log of 3.5 times 10 to the negative 8, plus the log of my base over the acid. The base is the OCl, or the ClO ions, which is coming from KOCl, so it's 14.4 over 3.75. And you should get 8.04 as your pH. Okay, that's working with acids. Now I want to do another example quickly with bases. Okay, calculating the pH of a solution that is 0.5 molar ammonium chloride, 0.3 molar ammonia. Now when they give you just these concentrations like this, they're already telling you that in the entire solution, when these things are combined together, that these are the molarities. And so it actually takes out the step of having to find out the millimoles. But you should know the equations are written fairly the same way as dealing with bases from chapter 14. I've got my NH3 plus, when it gets put in solution with water, HOH, I get NH4 plus, which that NH4 plus comes from ammonium chloride. The chloride gets canceled out there, and hydroxide ions. Okay, I have concentrations here. NH3 has a concentration of 0.3 molar. NH4 comes from ammonium chloride, which has a concentration of 0.5 molar. What you also need to know for this is the Kb. They'll give you the Kb value of NH3. Kb value of NH3 is 1.8 times 10 to the negative 5. Now, I can go ahead and use Henderson-Hasselbalch with this. My pH equals pKa plus the log of the concentration of the base over the concentration of the acid. The thing you have to pay attention to here is that when you're dealing with bases, this still is pKa. So I need to take this Kb value and do Kw over Kb to give me a Ka value, which with this one is 5.56 times 10 to the negative 10. So now I can go ahead and plug it in. pH is equal to the negative log of 5.56 times 10 to the negative 10 plus the log of, and then I'm already given concentration, so my concentration of the base, this is where you need to know, the base is NH3 is 0.3. My acid, anything that has a positive charge is going to be acidic because it has a hydrogen to get rid of. 0.5 molar. Those get plugged in, gives you the pH of 9.03. Alright, so let's go ahead and add strong acids or strong bases to buffered solutions and see what happens and compare it to what happens when it's not a buffered solution. So I'll give you a couple of minutes just to write down those just general rules to follow. And then we have 2 examples and then we'll be done. Okay, when we are working with, all we did up here was we were finding the pH of buffered solutions. Now we're going to go through and add stuff to the buffered solution. So again, a buffered solution is just something where it resists the change in pH. And the reason it can do that is because it's got a weak acid and it has its conjugate base there in significant amounts so that it prohibits the production of hydrogen ions or hydroxide ions if we add a base. And so we have to do a little stoichiometry first, then move on to equilibrium or using the Henderson-Hasselbalch equation. Again, buffer must have an acid and a conjugate base or a base and its conjugate acid. The partners must be on opposite sides of the equation. So in the next part, we'll do 2 examples, one adding a strong acid, one adding a strong base.